Hello everyone, in this video we're going to be focusing on gravimetric analysis and the different types of problems you'll encounter with it. So our first question is, what is gravimetric analysis? Gravimetric analysis is a chemical technique to determine the composition of ions in a compound or even the parts of a mixture. So we start with either a soluble salt or a solution. Now if we start with a soluble salt, we just add water to make it into a solution. So regardless, we're going to be using a solution in lab. In this particular diagram, we are trying to determine the composition of the lead in the original salt. To do this, we add a solution containing sulfate, right? It's probably going to be sulfuric acid that we add, right? So what happens is when we add the sulfuric acid here, the lead ions are going to combine with the sulfate ions to produce an insoluble solid, right? So lead sulfate precipitates out of this solution. We have to add an excess of the sulfuric acid so that all of the lead, that component that we want, precipitates out as the lead sulfate. The third step is to filter out that precipitate, so to filter the lead sulfate and then weigh it. Because what we're going to do is we're going to take the mass data and we're going to perform stoichiometry to figure out the amount of lead that was in our original salt. Now, gravimetric analysis is an extremely versatile technique. You could be asked to solve for a variety of different things like concentration of an ion or compound, identity of an ion or compound, percent composition of an ion or compound in an impure mixture, amounts, a bunch of different things. So I've got 4 examples that we're going to look at to solve for each of these. Okay, so our first problem is focusing on concentration. It says you discover 100 milliliters of barium nitrate solution of unknown concentration. You add excess sulfuric acid to completely precipitate solid barium sulfate. Once filtered and dried, the precipitate weighs 24.38 grams. What is the concentration of the barium nitrate solution? Okay, so the first thing we have to do here is write out the equation. So what's happening is we've got barium nitrate, 3,2. We're adding sulfuric acid, H2SO4. What's going to happen is we're going to see a double replacement reaction. So the barium is now going to combine with the sulfate. Both are charged +2, -2, so it's a 1-to-1 ratio. And then we're going to see the hydrogen combine with the nitrate to make now nitric acid. And I need to balance this, which looks like that's going to be A2. Okay, so the precipitate here is the barium sulfate on the right side. So I'm going to take the information I have, 24.38 grams of barium sulfate, and I'm going to use this information to figure out how much of the barium nitrate I have. I can do this because they share a common ion, barium to barium. So my first step is going to be to convert this to moles. So the molar mass of barium sulfate is 23.39 grams for every 1 mole. Okay. Now is where things get tricky, and this happens all the time in gravimetric analysis. For every 1 mole of barium sulfate, I need to see how many moles of barium I'm going to make. Well, there's 1 barium atom, so I get 1 mole of barium ions. Okay. So now I'm going to see how many barium ions I need to make 1 mole of the barium nitrate. And this is again just 1 barium atom. So 1 mole of barium ions will go to make 1 mole of barium nitrate. So you see how I went from the grams of my precipitate now to how many moles of my original salt I had. So when I do the stoichiometry, I get 0.1045 moles of the barium nitrate. Now the problem is asking me for concentration. So concentration is moles per liter. So I have moles, it's 0.1045 moles. Now liters, it gave me milliliters, so real quick at the bottom here, I'm going to convert milliliters to liters. That's going to give me 0.1 liters. Right. So 0.1045 divided by 0.1 gives me 1.045. If I'm paying attention to sig figs here, I've got 4 on the top, 1 on the bottom, which means I'm going to make that 1 molar. And that is my final answer. Our next problem looks into identifying an unknown. So a barium halide exists as a hydrated salt, BaX2.2H2O, where X is the halogen. A 0.2650 gram sample of the salt was dissolved in 200 milliliters of water, and excess sulfuric acid was added. The barium sulfate precipitate was filtered, dried, and found to have a mass of 0.2533 grams. Determine the identity of the halogen X. Well, anytime we're looking for an identity, I know I'm going to need molar mass at some point. But I'm going to start by taking my precipitate and finding out how much of my original salt I had. So we're starting with 0.2533 grams, and this is BaSO4. I'm going to convert that to moles. So 233.39 grams for every 1 mole. Now I'm going to find out how many ions of barium I get out of the barium sulfate. So 1 mole of barium sulfate gives me 1 mole of barium ions. Right. Now, looking at my original salt, 1 mole of the barium ions, this is going to be longer, gives me 1 mole of BaX2.2H2O. Okay. So this stoichiometry tells me that I've got 0.001085 moles of my original BaX2 hydrated salt. Okay. Now, the molar mass of the hydrate, really any molar mass, is going to be mass divided by the number of moles. So in this case, the mass of my original salt was 0.2650 grams. The moles I have are 0.001085. That's what I just solved for. So that tells me the molar mass is 244.24 grams per mole. Now that is of the entire salt. Okay. This does not tell me the molar mass of the halogen that I'm trying to identify. So, the molar mass of my salt, if I were to break it down, okay, it is the sum of the number of moles of each element, times the molar mass of each element. So let's take a look at our salt. I know the molar mass is 244.24 grams per mole. So my first element is barium. I've got 1 mole times the molar mass of barium, plus I've got 2 moles of whatever the molar mass of X is, plus I'm just going to lump all of water together, so I've got 2 moles times the molar mass of water. Little shortcut there. So if I fill in here, I've got 244.24 is equal to 1 times the molar mass of barium, 137.33, plus 2x, plus 2 times the molar mass of water, 18.02. When I solve for x, right, that molar mass is 35.44 grams per mole. That is the molar mass of just my halogen. So I pull up my periodic table, and oh, what do you know? I've got an element with a molar mass of 35.45, which is chlorine. And that's my answer. In our third problem, we're going to be looking at calculating the amount of different components in a mixture. As a result of a mishap, we have 0.7209 grams of a mysterious mixture containing magnesium chloride and sodium nitrate. We would like to know the relative amount of each compound in our mixture, which is fully dissolved in water. We add an excess of our precipitating agent, silver nitrate, and observe the formation of a precipitate, silver chloride. Once the precipitate is filtered and dried, we find that the mass of the solid is 1.032 grams. So our precipitate here is silver chloride. So the first thing I need to look at here is what ions are shared with the salts that I started with. So the only common ion I have is the chlorine ion from magnesium chloride. So the only thing I can get out of the mass of this silver chloride is the mass of my magnesium chloride, and that's where I'm going to start. So I've got 1.032 grams of silver chloride. I need to start by converting that to moles. The molar mass is 143.32 grams per 1 mole. Now I need to find for every 1 mole of silver chloride, I get 1 mole of chlorine ions. This next part's a little different than the problems we had before because magnesium chloride doesn't have just 1 mole of chlorine, it has 2 moles of chlorine. So I need 2 moles of chlorine ions to make 1 mole of magnesium chloride. And finally, I'm going to convert to mass. So molar mass is 95.20 grams in 1 mole. So that tells me that from the 1.032 grams of silver chloride, I had 0.2285 grams of magnesium chloride. That's the first part of my answer. But that's only one component. How am I going to find the other component, the sodium nitrate? Well, it's actually easier than you would think. I started with 0.7209 grams of this mixture. Well, if 0.2285 grams was magnesium chloride, I'm just going to take that out by subtraction. That means that I had 0.4924 grams of the sodium nitrate. And those are my answers. Our last problem is definitely the hardest one I'm going to show you. It says a 0.8870 gram sample containing only sodium chloride and potassium chloride was treated with silver nitrate. The silver chloride formed had a mass of 1.913 grams. Calculate the percent sodium chloride in the sample. Now on the surface, this seems pretty straightforward. If I want to calculate the percent of sodium chloride, I need to solve for the mass of the sodium chloride, divide by the mass of the sample, multiply by 100, and boom, I've got percent. The problem comes in with the fact that my precipitate is silver chloride, and I've got sodium chloride and potassium chloride. They both share a common ion with my precipitate. That means that I'm going to need to use a system of equations to solve this. So I'm going to start with, well, I've got 0.8870 grams of my sample. So X number of grams is coming from my sodium chloride, plus Y number of grams is coming from my potassium chloride. So I've got two variables here, X and Y. Ultimately, I'm going to want to solve for those X grams of sodium chloride to find the percent. Now this is different than our other problems because we're actually going to be working with variables and we're going to be working backwards. So I'm going to start with my X grams of sodium chloride. And from my X grams of sodium chloride, I want to see, well, how much silver chloride would get me that number of grams of sodium chloride. So I'm going to start by converting to moles, 58.44 grams per 1 mole. Now I'm going to say 1 mole of sodium chloride gives me 1 mole of my chlorine ions, and 1 mole of my chlorine ions gives me 1 mole of silver chloride. And now I'm going to go to mass. So the molar mass is 143.32 grams per 1 mole. Now when I do this stoichiometry, because I started with a variable, that same variable is going to stay with me at the end. So if I did 143.32 divided by 58.44, it gives me 2.452, remember it's times X, right? And that is grams of AgCl. Right, that is what I get from the sodium chloride. I'm going to do the same thing for the potassium chloride, but I don't want to use Y here. So instead, I'm going to rearrange my equation to solve for Y. So my Y grams of KCl is 0.8870 minus the X grams of the sodium chloride. So when I do this math, Y is now 0.8870 minus X grams of KCl. I'm going to go through the same process. First, I need molar mass, 74.55 grams per 1 mole. Now I find moles of ions. 1 mole of KCl gives me 1 mole of chlorine. 1 mole of chlorine gives me 1 mole of AgCl. Finally, molar mass, 143.32 grams in 1 mole. Now again, I'm going to take this expression, I'm going to multiply it by 143.32. I'm going to divide by 74.55, and instead of distributing in, I'm actually just going to leave the division here on the outside. I'm going to have to drop down here. It's 1.922 times the 0.8870 minus x, and that's grams of AgCl. So, what do I do now? What you can see here is I have 2 different grams of AgCl, right? Both with a variable x in them. And what do you know? I actually have the total mass of the AgCl that I got from my precipitate. So I can say that the 1.913 grams of AgCl is the sum of the 2.452x plus the 1.922 times 0.8870 minus x. Aha! I can now solve for x. And remember, x is my grams of sodium chloride. So 0.3928 grams of sodium chloride. Right? The hard part is done. Right? I finally got to my grams of sodium chloride. Now if I want to find percent mass, I get 0.3928 grams, that's my sodium chloride, over the mass of the sample, 0.8870 grams, times 100%, and it is 44.3% sodium chloride.